Hey everybody, in this video we are going to take a look at writing electron configurations, but this time using a special, faster type of notation called noble gas notation. It is a faster way than the typical long form type of electron configuration where you have to start all the way back at 1s every single time. If you've done enough of these things, you know that some configurations can be very long and it can feel tedious. So chemists, of course, tried looking for a faster way to pretty much get the same job done. To make my point about how tedious, long, and honestly repetitive electron configurations can be, let's take a look at a set of 3 different atoms that have been specifically chosen, starting with neon, which has 10 electrons. So if you wrote out those 10, it would look like this. Not so bad, right? 1s2, 2s2, 2p6. If I then asked you to do sodium, which has 11 electrons, of course those 11 would have the exact same beginning, 1s2, 2s2, 2p6. The only thing that would make sodium different and special and separate from neon is that extra 11th in the 3s1. And for magnesium, which would have 12, you would do all of the same things, 1s2, 2s2, 2p6. The only thing that really makes it magnesium is the 3s2, and we can see that effect is even more pronounced and longer and more tedious the larger our atoms get, right? Argon with 18 goes up to 3p6. Potassium with 19 just has one extra that ends up in the 4s1. But really what we're seeing is that it's just these final orbitals, right? The 4s2 and the 4s1, the 3s2 and the 3s1. It's just these that let us know what element it is we're even talking about. Essentially, these inside electrons, the ones that are highlighted here in blue and green, they're all the same, and that's the repetitive part of this configuration. So chemists said, since these inner electrons, let's call them, are so repetitive, right? If every configuration larger than neon starts with 1s2, 2s2, 2p6, could we not get rid of it altogether and come up with a faster way to write configurations that only show these orbitals on the end, that actually are the ones that identify what the atom is? And of course, that's what chemists came up with, and that is called noble gas notation. The way you do it is take noble gas element symbols and use them to represent larger chunks of electron configurations. I'll show you exactly how that looks with these 3 up here, and then walk through a format that you can follow. So first of all, let's talk about noble gases. If you're looking at a periodic table, the noble gases, we'll use this one in the top left, are the column of elements on the far right-hand side of the periodic table. In neon, this first one we did here with 10 electrons happens to be one of those. Noble gas notation says if you're doing any element larger than neon, you can take neon's element symbol, which is Ne, put it in this set of square brackets, and that Ne in square brackets represents whatever neon's configuration is. In this case, 1s2, 2s2, 2p6. So if you're doing sodium, you can just simply write Ne in square brackets, follow that Ne with 3s1, which makes it a configuration for sodium, and be done. Same thing here for magnesium. I could just do Ne in square brackets, followed by 3s2, and that would be the noble gas notation for magnesium. It doesn't matter so much for small atoms like neon, sodium, and magnesium, but if you're talking about larger atoms like potassium, which has 19, it might save you a pretty significant amount of time to be able to put argon, another one of our noble gas elements, in square brackets, and that would save you from writing out all of this. 1s2, 2s2, 2p6, 3s2, 3p6 is now summarized here with Ar in square brackets. So that's what these noble gas notations are going to look like, and that's why they exist. In order for you to do this, I'm going to give you a general format that you can follow. And this is how we're going to write it out. It looks pretty much like this, starting with the square brackets, which, if you haven't guessed yet, will be one of your noble gas element symbols. Again, that's from the far right-hand column of the periodic table. You can use any of those. Following that noble gas is going to be an s orbital. How do you know it's an s orbital? Because it will always be an s orbital. If you're taking notes along with this video, it's worth making a note of that. Following the noble gas notation, or the noble gas element symbol, it's always going to be an s orbital. Your job is to really know, like, which s. Is it a 2s, 3s, 4s, 5, 6, 7s, maybe even 8s? And the way you can tell which s orbital you're starting with after the noble gas is to use the row number of the element you're trying to write the configuration for. In other words, if you come up here to the top left, this would be row 1 or period 1, row 2 or period 2, 3, 4, 5, 6, and so forth. Whichever row number your element is in, that will be the same s orbital you start with after the noble gas notation symbol. And then after that, you follow the typical orbital filling order as you normally would, using an Aufbau diagram or the diagonal rule or any other method that you have. Let's go through some examples so you can see exactly how this works, starting with chlorine. So here's chlorine on the periodic table. It's got 17 total electrons, and I'm also going to point out that chlorine is in the third row, right? That's going to matter for how we do this. Chlorine is in the third row with 17 total electrons. I'm going to make a note of how many electrons we have to put in, 17, and also that chlorine is in period 3, or the third row of the periodic table. The next thing I've got to do, or the first thing I guess, is decide which noble gas to use for my noble gas notation. I'm going to bring back my periodic table now so we can talk about how to make that decision. The easiest way to do it is to find your element again, so here it is, chlorine, and count backwards until you land on a noble gas, right? 17, 16, 15, 14, 13, 12, 11. Finally, I land on the noble gas neon at 10. Neon will be the noble gas that I put in square brackets. You could technically use helium, but helium only represents 2 measly little electrons and it doesn't save you a whole lot of time. Neon would be much smarter because it represents 10 of chlorine's 17. You also can't do anything larger than chlorine, like argon, because argon has 18 electrons more than chlorine has in the first place. So anything larger than chlorine, all of these down here, doesn't make any sense at all. So neon is the one that we're going to use. So my noble gas notation begins with square brackets and the Ne symbol inside those square brackets. Following the noble gas symbol will be an s orbital. You know it's an s because it is always an s orbital. The way that you can tell which s orbital, is it 1s, 2s, 3s, 4s, or so on, is the row that chlorine is in. We've already established chlorine is in row 3, which means I'm starting at 3s. S's, of course, can hold 2 electrons, and I just keep counting up from here following my typical orbital filling order. I like to come up with this order using the diagonal rule, which tells me 1s gets filled first, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, 4p, 5s, and so on. You can check out more detail on that in the prior video to this one. The point is, after the 3s orbital, if I follow my arrows, comes the 3p orbitals. And I've also got to remember that I'm only going up to 17 here. This neon symbol accounts for 10 electrons out of those 17. The 10 is how many electrons neon has. So with my 3s2, that was 12 electrons, and to get up to 17, my 3p orbitals only need to have 5. That would be chlorine's noble gas notation. Let's take a look at a much larger element, and this is really the reason why noble gas notation exists. This time we'll do technetium or technetium, depending on who you are and how you say it. So here's my element, Tc. It's got 43 total electrons, and notice the row number that it's in, row 5. So we need those two pieces of information. Let's also choose the noble gas that I'm going to use here for technetium by counting backwards from 43 until I land on the noble gas krypton Kr, which has 36 total electrons. So we'll begin by putting Kr in square brackets, followed by Ns orbital. Remember, technetium was in row 5, so that means I'm starting with 5s, which holds 2. After the 5s orbital, I'm going to follow my arrows up here on the diagonal rule, which tells me after 5s comes 4d, then 5p, and I didn't go down far enough, but if I had to keep going, 6s would come next. The point of this one is that after the 5s, we would start filling the 4ds. Let's keep track of our electron totals as well, right? Krypton has 36 electrons, so this Kr in brackets represents 36. For technetium, I only have to get up to 43 total, so I don't have very many to go here. The 5s2 gets me to 38, which means to get up to 43, I only need 5 electrons in those 4d orbitals. And this would be the noble gas notation for technetium. I've got 2 more practice ones in this video. Ideally, you would pause the video to try these yourself first before you click play again to watch me go over the answers. Assuming you've done that, or if you just want to follow along for some more examples, here we go. I'm going to do these a little bit faster now, starting with niobium Nb. So here's niobium. It's got 41 total electrons. If I count backwards from 41, I'm going to use Kr again in my square brackets, and Nb is in row 5. So for Nb, we're going to start with Kr, that represents 36. After Kr is going to come 5s2 because niobium is in row 5, and that gets me to 38 electrons, which means in the 4d orbitals, I only need 3 more to get up to niobium's total of 41. If we try this again with lead, our largest element yet, here's Pb, lead. It's got 82 electrons. Pb is in row 6 of the periodic table, and if I count backwards from 82 to choose a noble gas, I land on xenon Xe54. So in my square brackets goes Xe, and I'm going to keep track here because these numbers are getting a little bit big. That is 54 total electrons. The s orbital that comes after Xe is going to be the 6s, because again, lead was in row 6. 6s, of course, can hold 2. Following the 6s orbitals, if I go back to my diagonal rule, comes the 4f, then the 5d, and again I didn't go far enough down. This would be the 6p and the 7s, which would come next. So now I've got the order that I'm going to follow. After 6s would come 4f, then the 5ds, then the 6ps, then the 7s's. Sometimes I just write them all out in the proper order before I start filling in the electrons. Alright, so 6s2, 4f, F's can hold 14 total electrons, D's can hold 10 total electrons. All of this is because lead has 82 total that I've got to get up to. The 6s2 gets me to 56, the 4f14 gets me to 70, the 5d10 gets me to 80. So to get up to 82, my 6p orbitals have to have 2 electrons, and I can erase the 7s's because I don't actually need to go that far. So that's how you do noble gas notations. That also wraps it up for this lesson. Thanks a lot for watching.